In this video, we're going to learn about the exponential distribution. Time is a non-negative and continuous random variable. Many risks involve the measurement of time between an initial point of time and the occurrence of some phenomenon of interest. Some temporal situations that we encounter in risk assessment include things like the lifetime of individuals, or the lifetimes of mechanical, biological, or social systems, waiting times for service, learning times for animals or individuals, durations of epidemics, traveling times for buses, trains, planes, and so on, breakdown modeling, the time until the next flood, the next earthquake, or the next natural disaster. So for an example, an emergency worker is given a task to perform. How long will it take to complete the task? Very often the phenomenon of interest is the failure of some system or a system component. How long before a pump or generator motor will fail? How long will the chain on a dam's gate last? How long before a security person makes a mistake? The phenomenon can also involve recurring activity like the length of time between towboats appearing at a lock, the time between outbreaks of foodborne illnesses, the duration of phone calls, or the duration of a doctor's visit, and so on. So these are examples of situations where an exponential distribution may be useful. The exponential distribution, we look up here at the density function, we see it has one parameter, a beta. X would be your data, E is a known constant, and so we need one parameter to fully specify this distribution. So imagine that we have some data here. Perhaps it's the time between customers. So from A15 through A44 we have a bit of data. It turns out to estimate beta, all you have to do is calculate the average of your data. The mean of your data is the beta parameter of the exponential distribution. So let's do that. We grab our data, calculate, and the beta is 10.08. We'll just round that off to 10 and create a exponential distribution here. Already at 10, that's good, and we say OK. And so now what we have done is with this little bit of data, we have enabled ourselves to specify the probability for any situation. You can see now that our data, the distribution goes well beyond the limits of our data here. As I look quickly through our column, it looks like 31 may be the largest value that we've observed. So fitting the data to a distribution enables us to extrapolate to the probability of events beyond 31. If we'd like to know what's the probability that it takes 40 minutes or more for a customer to arrive, there's less than a 2% chance of that. And if we wanted to construct a model where we were looking at if we were going to construct a model where we were looking at the time to the next customer, all we have to do is hit our F9 key and see it could be 17 minutes, it could be 11, it could be 39, and so on. The exponential distribution is a right-skewed distribution. It's bounded at 0, and it has only one shape. So let's consider a few examples. I'm going to move us down here now, where I've inserted an exponential distribution that has a beta of 1. So that you can see how the shape changes, I'm going to add another exponential distribution here, and this time I'm going to let the beta be 2. The beta is not required to be whole numbers, that's just for our convenience. So you see now the red distribution has increased the likelihood of larger values. And if we add one more just to complete the example, I could make the beta a 3. and you see the green distribution now, so that the values between 0 and 2 are less likely in the green than they are in the red, and they are less likely than they were in the blue. But in trade-off, the larger values are all more likely. But every distribution has exactly the same shape. The parameter beta is the mean time. It's the mean time until the occurrence of the next event, and it represents the waiting time for the first occurrence of a process, which is continuous in time and of constant intensity. That's a little bit tricky. This constant intensity condition requires a little bit of our attention here. So let me scroll on over, and we're going to be looking up here for a few minutes. Constant intensity means the average time is not changing. This can lead to a really interesting property of the exponential distribution. So suppose the average life of a light bulb is 1,000 hours. So we have here the mean life of a light bulb, and if I open up this distribution, you can see it has a mean of 1,000. Now suppose we have a light bulb that has been burning for 350 hours, or any other number of hours. Point being that it's been on and burning for a while. Then if we would like to know what is the distribution of the time for this light bulb to burn out, given that it has been on for 350 hours already, then the answer is it's exactly the same. It is an exponential distribution with a mean of 1,000. A light bulb that has been burning for 350 hours has exactly the same average lifetime as a light bulb that has just started burning. This is the idea of constant intensity, and it's not an easy one. What all this means is this. If we ask how much longer we have to wait for this light bulb to burn out, given that it's been burning for 350 hours, we can basically forget that it started 350 hours ago and act as if the experiment is just now beginning. This is what constant intensity means. In this sense, we say the exponential distribution has no memory of the past. It is a memoryless distribution. The exponential distribution is the only non-negative, continuous random variable distribution to have no memory. So here we have a light bulb that has just been turned on, and its average life expectancy, or the simulated expectancy of this light bulb's life is 785 hours. Here we have a light bulb that's been on for 350 hours, and it has a simulated life expectancy of 767 remaining hours. So you can see how that might change. Here we just had the dumb luck where both of them pop and go out quickly. Here the new light bulb has a very long life, the one that's been on relatively short, and then there by dumb luck it just reverses. This is the nature of an exponential distribution. If you have a process or a system where things wear out or where they burn in, causing the failure time to increase or decrease because of the wearing out or the burning in, then the exponential distribution is not a good choice for these situations. So for example, the belts on your automobile engine, they clearly wear out, and the older they get, the more likely failure becomes. These are increasing or decreasing intensity failures. You wouldn't use an exponential distribution for something like that. An electronic component, on the other hand, like a light bulb, something that just goes pop rather than wears out, is called a constant intensity failure. The exponential is only good for constant intensity failures. Now let's take a look at this distribution once again. This is 1,000, and this is a density function view that we have here. So if we go back to the data here that you were looking at, what I did was used a beta of 10, and I just put in some dummy data here. You can follow that column down. And I calculated the density function value corresponding to 1 when beta equals 10. So this column right here, you see this function. This function is exactly the function that you see in the upper left of this spreadsheet when you open it. These points here are plotted in this graph here. Let me move this aside for you. So this is a plot of the exponential with a beta of 10. What I would like you to understand is this: these values here, they have no probability interpretation. This does not mean the probability of 1 is 9%. These numbers just enable us to scale the drawing and to make it plot well. So notice the values here. You see about a 0.1, and over here you see the same 0.1. So when you're dealing with density functions, this vertical dimension has no probability meaning. You cannot interpret it. These are just numbers calculated that help us scale the drawing. What we are going to do, however, is right mouse click and choose the cumulative ascending. We can look at the data in different ways, and that's what we're going to do now. So let me cancel this, scroll to the right a little bit, get that centered for us. Now, what you're looking at here, this is the capital F of x, the cumulative distribution function. This gives the probability that the system or component dies before x units of time have passed. But let's take that back to our light bulb. This is basically saying if we have 500 hours of life, the probability that a light bulb will die before 500 hours passes is 0.4. The probability that a light bulb will die before 1,000 hours, looks like it's about a 0.61 or 0.62. So you can grab any value here that you care to use. The probability that a light bulb will die before 2,000 hours, that's getting pretty close to 90%. Okay? So if we take 1 minus capital F of x, or 1 minus the cumulative distribution function, then we have the probability that a system or a component survives more than x units of time. That's what we're showing here. So this is an ascending cumulative distribution function. This is a descending cumulative distribution function. Here we have 500. The probability that a light bulb will die before it reaches 500 hours is 0.4. Over here we have 500. The probability that a light bulb survives at least 500 hours is 0.6. So you notice this is the complement. And as I said, this function is sometimes called the survival function, and survival functions can be very useful in risk assessments as well. So I'm going to end on a little bit of technical jargon here. And that is to say, in general, if we believe that a random variable x is the result of a process of growth or duration or increase for which the strength of the forces that act probabilistically to control the processes, if they are at all stages of the process independent of the growth, duration, or increase already achieved, then x has an exponential distribution. Its density function is given here. Its cumulative distribution function is given here. This is a very useful curve for risk assessors. Please feel free to ask questions in class if you have any.